Hey everyone, Chang here and welcome to my channel. Now, this video is going to be slightly, I guess you could say, weird or interesting. Now, I'm not sure where to put this. This is not really in any sequential order. There's not really any, oh my god, this is one specific topic. But there are 5 properties that are in algebra that I found if I had been introduced to it sooner, if I remembered it, recalled it when I really needed it, it might have been actually helpful. A lot of these properties are usually used in a sort of more challenging kind of problems, hoping that you either recall it or somehow are able to derive or figure it out. Now, these 5 properties are not mandatory and for you to succeed in algebra or whatsoever, but there will be occasions where you're going to encounter problems that you might need to use them, or especially when I encountered them, a lot of proofs that would make your life a lot easier if you just can recall or use it to your advantage. I'm not going to go into details on how each and every one of them can be used, but I'm hoping that by the end of this video, you've at least seen it before, have sort of this in the back of your mind so that when you encounter problems or when you happen to see them again, it will jog your memory. You'll be able to use it. It will make your life a lot easier. And you know, it's just something that is really cool to see once in a while. It's listed in textbooks and all that stuff, but unless you really read a textbook page by page, you might just have skimmed over and completely forgot about it. So here's 5, I guess you say, uncommon or not emphasized property that I feel like are extremely important in algebra. All right, so for the first one is this one right here, the law, right? Law of trichotomy. Now, when we read it and we understand it, yes, it's extremely obvious. We have it sort of unconsciously ingrained, but never really think about it. So this one, the law of trichotomy, is actually fairly simple. It's saying that for a and b as an element of the real number, basically a and b is any number that we're normally working with minus the complex numbers, right? A and b must be related as at least one of the following. So that means it has to be at least A is going to be less than B, A is greater than B, or A is equal to B. So it has to be at least one of these guys, right? There's not going to be a situation where none of these guys apply. Now, why is it important? Well, when I first encountered this law, right, it was actually used as a way of proving. So when you prove something and you want to show that they're either greater than, less than, or equal to, you eliminate the other 2 possibilities. So if I wanted to show A and B are equal to each other, what I would try to do is I want to show that A is not less than B, like that statement is false, and A is not greater than B, that statement is false. So if these 2 are false, then by the law of trichotomy, it has to be A equals B. And of course, you can mix up the variation. If these 2 are false, then it has to be this relation. If these 2 are false, then it has to be this relation. So even though it sounds obvious, when it's not put into words, when you don't see it explicitly for the first time, you don't realize how powerful this really is. This I found is extremely useful for proofs. Alright, so for our second property, it's called the triangle inequality, and there's 2 variations. There's the regular triangle inequality, and then you have the reverse triangle inequality. The top one right here is the triangle inequality. Bottom one, you can guess, is the reverse triangle inequality. Now, when you look at the statement, actually it sort of makes sense. First and foremost, if you have the absolute value of A plus B, it's going to be less than or equal to the absolute value of A individually plus the absolute value of B individually. Now, how does that work? Well, if A and B, for some reason or another, if one is going to be positive and one's going to be negative, guess what? It's going to start canceling each other out to a degree, and the number should be smaller than if you take both of them, right? Even if it ends up being negative, you're going to take the absolute value of it, it's going to be positive. So you're going to have 2 positive variations and add together. That should be bigger, if not equal exactly to what happens when you actually have them cancel each other out, right? So by that same logic, this is the same thing. A, or the absolute value of A minus B, is going to be greater than or equal to the absolute value and the absolute value of the inside A minus the absolute value of the inside B, right? So the reason for that is, well, fairly simple. Let's just say, for example, A is a positive number and B is a negative number. So if you have a minus negative number, it becomes positive, right? So this actually is pretty large. But if you take the absolute value of each of them individually, they become 2 positive numbers. So you have one positive number minus another positive number. So it can't get bigger, it only can get smaller. So therefore we have that greater than or equal. Now, this one, normally you can use it in, like, for example, geometry, right? The whole purpose of this is to say that well, guess what? One side cannot be greater than the sum of two other sides, or it won't, close as a triangle. That's why they call it a triangle inequality. But of course, the most prevalent that I've seen used in this is actually for, I guess you could say, the proof in calculus, right? The delta epsilon proof is what they want to call it. Usually these are really good at limiting your factor and showing that because the behavior of, I guess you could say, one function is bounded by the behavior of two other functions, therefore you can assume that as they get to a certain area, then it's going to be, that specific number. Now, that's a little more advanced and not something that we're going to cover in details, at least as of right now. But it's also a good idea just to know that there's such thing as the triangle inequality and the reverse triangle inequality. Because guess what? There are going to be situations where it's not going to be in calculus. They expect you to know this or use this as sort of a challenge type problem. And of course, since you've seen it before, hopefully you can recall it and you will kick that problem's ass. Now, this third property is actually extremely obvious. There's not even a name for it, but I think it's really cool because it actually explicitly shows you how to get rid of absolute value when it's not necessary. Now, the only reason it works is because the exponent happens to be an even number. We know at this point that if an exponent is an even number, whether the base itself is a positive or a negative number, the end result is still going to be positive, right? Because if you have two negative numbers and they multiply together, guess what? The negative cancels. So that utilizes this idea. You have the absolute value, which usually, whatever you put in there, you're going to get the positive variation of it. So, absolute value of a squared. Well, guess what? Anything squared is already going to be positive. So it's almost sort of, I guess you could say, redundant in the way of ensuring that it's positive. It doesn't mean that the square itself is irrelevant, but it's redundant in whether controlling the outcome as positive or negative. So we have the absolute value of a squared, and a could be a number. It could actually be a algebraic expression as well. So that's where I think it's really cool, right? So if you have an absolute value and you have some number or some algebraic expression squared, right? Technically, that's the same as if you take the square on the outside, right? Because guess what? This is still going to be positive. Whether you square the inside or outside, the end result is still positive. So that's why we have this. And of course, now at this point, it doesn't matter. It's redundant. The absolute value can just be taken away and you can have it equal a squared. This is really good for situations where you have an absolute value that's sort of thrown you off, but you see that inside, not just a part of the inside. So don't get that mixed up. You don't want it to be a situation where, let's just say, for example, you have absolute value of a squared plus b squared or something like that. That's very different, right? That means, it's not the same thing. So here's the thing. If you have something like this where the entire expression is squared or the entire number is squared inside the absolute value or even to the fourth power or sixth power, as long as it's an even exponent, you can actually take it out and get rid of the absolute value entirely. This is definitely something that I think would be a fun sort of a trolling kind of problem for teachers to give to their students. And of course, now that you've seen this video, you're going to conquer it. All right, so for the fourth property and actually the fifth property, they're very similar that it often gets mixed up and a little confusing. Hopefully I can clarify it a little bit. Now the fourth one is just basically a square or cube of binomials. So here you can see, well, these are square because, they're exponent of 2 and these are cube, exponents of 3. Fairly easy. If you decide to distribute everything, you have u squared plus 2uv. So whatever you put in for u, whatever you put in for v, and then at the end v squared. Now, u and v you can put in whatever. It could be just a regular variable, right? X, y, z, whatever you want. Or it could be a variable with a coefficient in front of it, 3x, 4y, 5z. Or it could just be numbers. The idea is that after you distribute everything, this is the structure or the property that it follows, right? You have the subtraction variation as well, where you have u minus v. It's just going to be u squared minus 2uv plus v squared. That's simple. Now, for the cube, same thing. If you distribute everything, this is the long-winded way of doing it. Right? You have u cubed plus 3u squared v plus 3uv squared, and then plus v cubed. Same thing, except for now you have minus here and here. So if you don't want to memorize it, great, right? You can definitely always just distribute, and I would sometimes recommend that because guess what? If you're careful, less likely to make a mistake than if you accidentally memorize this incorrectly. Now, if you wanted to memorize it, what I would recommend is actually know the, what do you call that? The Pascal's triangle. You have the 1, 1, 1, and then 1, 2, 1, 1, 3, 3, 1, and so on and so forth, and it keeps going on and on. Now, here's the thing though. Notice the difference, and I'm hoping that I'll be able to point out just the slight subtlety. Here, technically, you have 1, 2, 1, 1, 2, 1. Same thing here, 1, 2, 1, 1, 2, 1. But since this is a minus, right, you have a negative sign there. So that's the difference, right? In order to memorize this, I want to say always look for an alternating pattern. I think it's more obvious with this right here. Now, if they're all positive, great, right? Because the next row right here is going to be 1, 3, 3, 1. Well, there you go. 1, 3, 3, 1. And of course, at this point, your exponent sort of varies. You have your cube, then this one loses 1 and this one gains 1. You can think of this as v to the 0 power, right? Now it's going to be v to the first power. Now, the next one, this one loses an exponent, the next one gains an exponent. So you have u and then v squared, and then afterwards u loses all his exponent, which is u to the 0 power, and then you have v cubed. Okay, so that's one way to remember it. The other thing is when you have the subtraction sign, notice that it's always going to be an alternating pattern. Positive, then negative. Positive, then negative. If you go down here to the fourth row where you do u minus v to the fourth power, it's just going to be positive, negative, positive, negative, positive, right? It goes the same thing, I guess you could say, above, right? 1, 2, 1, it's going to be positive, negative, positive. So that is a way to remember this. I mean, that's a lot to memorize, but if you guys got it right off the bat, it's a lot easier than having to manually distribute everything. All right, so here's our fifth property, sum and difference of cube. Now, that's why I'm a little worried when I say that fourth and fifth property tend to get intermingled or mixed up a little. Here's the thing. For this one, I do recommend you actually memorize this because there will be occasions where you encounter this, and if you wanted to factor it out, you can work on it, you can try it, you know, try different things, but to be a time saver, just remember this as well. Now, the easy part is that whatever is adding or subtracting, the first part is simple. If this is u cubed plus v cubed, then it's going to be u plus v, right? If it's u cubed minus v cubed, then it's going to be u minus v. The difficulty or the possible confusion is the second part. It's actually the opposite. If this was plus, make sure that you have this as minus, and if this was minus, you make sure you have this as plus. Now, if you memorize it, great. And if you are afraid that you might have accidentally memorized it incorrectly, always double check, right? When you get to this section, when you write it all out and you have extra time, definitely distribute everything and see if you get this as the end result. Now, that's why, once again, I'm a little worried about this, but I do think you should memorize this and remember the strict difference between sum and difference of cube and the idea of squaring and cubing of binomials, right? All right, so there we have it. 5 properties. They're not secrets in any way. They're always found in textbooks. The only problem is that unless you're really sitting down and reading page by page through these textbooks, often you will probably skim or not even realize these 5 properties. Are they that drastically important that you have to memorize them or you will fail in algebra? No. But I do find that on occasions, usually special occasions or specific kind of problems, you never know when these become useful. And just by being able to recall them, just having that inclination that these exist can save you a tremendous amount of stress and time. So hopefully these are just something interesting that you've seen or not seen and now know, right? It's not gonna, I guess you could say, affect your performance very negatively if you don't, but if you do, guess what? Most of them I've encountered in higher level when we're proving things in calculus or just general proof, and hopefully these will be useful as well. So thank you for watching this video. I understand it's a little different. Please like, comment, and subscribe. I will see you in the next video.